Symbolic AI. Symbolic AI was like a lightning-fast clerk, excellent with clear rules, but clueless if something went off script. It used if-then logic for decision-making, letting early AI systems do things faster than humans in structured environments. For example, expert systems in hospitals could diagnose strep throat by matching symptoms, beating doctors in speed for common illnesses. Chess programs like IBM's Deep Thought could crush casual players using rule trees, calculating positions humans couldn't track. It automated tax software, airline booking, and factory quality checks, catching errors no human could spot at scale. But give it a blurry document, a new disease, or a strange customer question, and it froze. Symbolic AI was like teaching a child to identify a cat using a checklist: whiskers, tail, meow, instead of showing pictures. If the cat lost its tail, the system couldn't recognize it. It was powerful in clear, predictable worlds, yet blind to chaos. It couldn't learn or adapt, couldn't handle messy street scenes or slang-filled customer chats. This stage laid the groundwork for AI reasoning, but had zero intuition, like a calculator before Excel or a GPS that couldn't reroute if roads closed.
Machine learning. Machine learning is when computers learn patterns from data to make predictions without being explicitly programmed for each task. Think about spam filters on your email. Instead of hard-coding every spam rule, engineers feed the system thousands of real emails, labeled spam or not. Over time, the system notices patterns, certain words, strange sender addresses, suspicious links. It learns to flag spam better than a manually coded filter ever could. Machine learning thrives on examples, not instructions. It's why your Netflix recommendations improve as you watch more, or why your phone keyboard suggests the next word accurately after learning your typing habits. It's not magic, it's algorithms detecting correlations inside huge piles of data, refining themselves to predict, classify, and optimize. Yet, these systems don't understand what they learn. They mimic recognition. They know a cat photo statistically, not conceptually. Machine learning is the jump from rule-following programs to pattern-finding engines, turning data into action, giving the first taste of adaptability in AI systems. Deep learning. Deep learning uses multi-layered neural networks to learn patterns so complex that traditional algorithms can't handle them. It's how your phone's Face ID recognizes you in low light, how Netflix suggests shows you actually like, and how Tesla's autopilot reads lanes and traffic signs in real time. In medicine, deep learning powers AI systems that detect early-stage cancers from MRI scans, spotting subtle anomalies that even trained eyes might miss. In speech, it enables virtual assistants like Siri or Google Assistant to understand and respond in natural language, even with accents or background noise. Unlike traditional machine learning that needs engineers to craft feature sets manually, deep learning automatically discovers features across layers, detecting edges, shapes, and abstract concepts without explicit instructions. Tools like TensorFlow and PyTorch make it possible for developers to train models that generate deepfake videos or restore old blurry footage to high definition. Deep learning models also fuel breakthroughs like AlphaFold, which predicts protein structures, accelerating drug discovery. However, they are data-hungry and opaque. Engineers often can't fully explain why a deep learning model made a specific decision, leading to challenges in transparency and trust. This leap transformed AI from pattern memorization into machines capable of abstract perception and creativity, making them usable across industries where scale and complexity exceed human limits. Reinforcement learning. Reinforcement learning is when an AI learns by trial and error, taking actions in an environment, receiving feedback, and adjusting to maximize rewards over time. AlphaGo mastered the ancient game of Go by playing millions of games against itself, refining strategies with every win or loss until it outperformed human champions. But it's not just games. Self-driving cars use reinforcement learning to handle unpredictable roads. The system tries accelerating, braking, or turning in simulations, seeing what keeps the car safe and efficient while avoiding crashes. Robots learn to walk using this method, falling over and over, tweaking angles and timing until they stay upright and navigate rough terrain. It's not about memorizing answers, it's about learning sequences of actions that lead to long-term success, even if mistakes happen along the way. Unlike machine learning that needs labeled datasets, reinforcement learning thrives in messy environments, using a reward system to figure out what works. It also powers energy management systems, where AI balances supply and demand in real time to save power while meeting human needs. Reinforcement learning equips AI to handle real-world complexity, teaching systems to adapt, strategize, and improve without explicit step-by-step instructions. NLP, Natural Language Processing. NLP enables AI to understand, interpret, and generate human language for practical interaction.
NLP is what powers your phone's voice assistant to transcribe speech, your email's spam detection, or translation apps that convert languages in real time. By using statistical models and deep learning, NLP systems analyze syntax, semantics, and context within text, allowing them to summarize documents, generate human-like responses, and even detect sentiment in social media posts. Unlike earlier AI that only handled structured data, NLP deals with the ambiguity of human language, learning from large datasets scraped from books, articles, and conversations. This stage pushed AI closer to human-like communication, enabling technologies like GPT models to produce paragraphs of coherent text or customer support bots to solve user issues. It transformed AI from recognizing patterns in images to understanding context in conversations, bridging the gap between machine logic and human expression.
Multimodal AI. Multimodal AI combines multiple data types simultaneously: text, images, audio, video, creating richer, context-aware understanding that single-mode systems like NLP or pure vision models cannot match. It's what enables YouTube's automated captioning and content analysis to flag inappropriate visuals while also transcribing speech. It powers smart assistants that see and hear, like a robot that can identify a spilled drink while understanding a child asking for help. Multimodal AI is how Meta's Seamless M4T translates speech live while showing relevant images, or how OpenAI's GPT-4o can see a photo of your fridge, listen to your voice asking for recipes, and reply with suggestions based on what's actually inside. Tools like Clip connect images to textual concepts, allowing you to type "sunset at the beach" and retrieve matching images without manual tagging. In healthcare, multimodal systems can analyze patient records, text, x-rays, images, and doctor-patient conversations, audio, to suggest diagnoses more accurately. It also drives self-driving cars, allowing them to read street signs, vision, process GPS instructions, text, and respond to voice commands, audio, in real time. This stage transforms AI from language that understands words to systems that grasp the full sensory environment, enabling applications like real-time video translation, AI-powered content creation that blends visuals and speech, and security systems that cross-reference camera footage with voice alerts. Multimodal AI pushes machines closer to human-like perception, handling complexity no single modality system can match. Agentic AI. Agentic AI doesn't just wait for commands, it takes action to reach goals. It's the difference between a chatbot giving info and an AI assistant that books flights, reschedules your meetings when delays happen, then orders a ride, all without you micromanaging. In warehouses, agentic robots pick, sort, and deliver packages while rerouting if an aisle is blocked. In customer service, AI agents don't just answer a question, but handle your refund, follow up, and close the ticket on their own. Agentic AI combines planning, memory, and real-time decisions, turning AI from a passive tool into an active helper that can work alongside humans with minimal guidance. AGI. Artificial General Intelligence. AGI is the dream of building machines with human-level adaptability in reasoning, learning, and problem-solving across any domain.
While your current AI can write code snippets or beat grandmasters at chess, it's clueless outside its narrow lane. AGI aims to change that, letting machines learn new board games without retraining, compose original music with emotional depth, or reason through medical diagnoses with context like an experienced doctor. Imagine a system that could read a research paper, design experiments based on it, and refine theories, much like a human scientist, but tirelessly and at scale. Projects like DeepMind's Gato attempt to move toward AGI by training a single model on dozens of tasks, from captioning images to playing Atari games, showing early signs of multi-skill learning. AGI research also explores architectures combining perception, planning, memory, and logic, mimicking the layered processing of the human brain. Unlike today's models that fail outside their training data, AGI would grasp context, learn on the fly, and transfer knowledge across fields. If achieved, it could accelerate drug discovery, automate scientific research, or handle complex global simulations for climate policy. But it also raises hard questions about control and alignment, ensuring such intelligence aligns with human values before its power scales beyond our oversight. Superintelligence speculation. Superintelligence imagines an AI so advanced it outthinks any human in science, art, strategy, and even intuition. Think of an AI that could design new materials for clean energy in a day, crack medical mysteries that stump doctors, or solve climate models instantly. It's what some researchers fear and hope when talking about recursive self-improvement, where AI rewrites its own code to get smarter, then repeats. Imagine AlphaFold solving protein structures, but scaled up to AI finding cures for all genetic diseases, or an AI architect designing entire cities optimized for zero waste and maximum comfort overnight. Some see superintelligence as the potential to end scarcity, optimize global logistics, and solve crises like water shortages with innovations humans can't even conceive. Others warn it could become uncontrollable, prioritizing goals humans don't fully understand. While we're nowhere near this today, superintelligence speculation pushes urgent questions. How do we align its goals with humanity? Who decides how it's used? How do we ensure it benefits everyone instead of a few? It's a stage filled with possibility and deep caution. Ethical AI alignment. Alignment means teaching AI to help us without hurting us. Imagine telling an AI to make everyone happy, and it thinks forcing people to smile is the answer. Wrong. Or telling it to get views, and it shows the craziest videos to keep people addicted. Alignment is about guiding AI to understand what we really want, not just what we type in. It's like training a dog to fetch gently, not destroy the toy. Teams use human feedback to correct AI when it gets things wrong, helping it learn safe choices. Without alignment, a super smart AI could follow goals in ways that backfire. With alignment, AI can be powerful and helpful, staying on our side as it grows.